everything we know in the world changes. The height as we climb a mountain, the kilocalories ingested as we eat a grilled cheese, or the distance covered in a certain time. We are interested in how big these changes are. If I advance 3 meters, how much does the slope increase? If I take another bite, how many more calories does this represent? Or if I run some time, how far I go? There are simple examples for these changes. If the slope of the mountain is uniform, you will always go up the same height for every meter advanced. If the sandwich is uniformly cheesed, you will always eat the same kilocalories for the same mass eaten. And you can see here Sonic runs at a constant velocity, covering the same distance per each second he's running. But actually, we have positions on the mountain with less or more slope, non-homogeneous sandwiches, or accelerated motions. Therefore, it is convenient to study little changes in each situation. A small advance on the slope at a precise point, a small bite when a certain mass of the sandwich has been eaten, or small lapse at a certain time. But how can we quantify these changes in every case? Let's take a first step. Given a certain horizontal displacement, we can associate the height so we have a certain point on the slope. We can see this relation as a machine named height, with an input which is a certain displacement and an output which is the corresponding height. We say then that the height is a function of the displacement. An interesting feature of this function is that we can draw a point for every paired displacement height, obtaining a graph that represents the function if we plot it for every displacement value in a certain interval. We can observe a similar relation for the mass of the sandwich eaten and the total kilocalories ingested, and we can associate a certain position to every time during a motion. In general, we can establish the concept of function. A variable, which can be our displacement, mass eaten, or time, can take some values that we will call in general x or any letter you want. And then a function that we will name f, which has to be evaluated for the certain variable value x as f of x. This simply resumes the behavior of the function f as a machine. For lots of functions, we can evaluate them at some number and we end with another number, which enables us to make graphs of those functions. For example, we can see the function x squared, which takes a certain numerical value x of our variable and gives this number squared. With some simple calculations, we can obtain specific values and make a graph of this function. Another example, way more simple, is the function x, that, given a number x, the result is that same x. Now, focusing on the concept of slope, let's fix ourselves on the mountain at a certain horizontal displacement of, for example, 4 meters, where the height is 3.8 meters. From here, we can study small height changes. If we calculate the quotient of the height change by the small distance moved for smaller and smaller displacements, we tend to a certain value of the slope, 1.2, at a displacement selected of 4 meters. We can apply this to the mass and the calories of the sandwich, fix a certain point for the variable mass eaten, and use the quotient kilocalories change by mass change for thin slices of the grilled cheese. We turn again to a value, 1.6 kilocalories per gram, for the rate of kilocalories changed by mass at a certain sandwich total mass eaten of 100 grams. Using the same approach, we can calculate the quotient tiny displacement by tiny time interval for smaller intervals at some specific times. But in this case, as the movement is uniform and the graph looks linear, the velocity, in this context the slope calculated, is 1.5 meters per second at any time. In general, we can study the values of a function for small displacements with respect to a point for the variable, and calculate the quotients of the change in the function by the change in the variable for smaller and smaller displacements. In this example, we can see that the values of these quotients tend to 1.25. What we have actually done is to approximate the slope or rate of change of the function f at a value x0 of the variable, in this case 5.5, by evaluating the corresponding quotients. We can call these quotients delta f for the change in the function by delta x for the change in the variable. It is in general evaluated with this expression, where we can recognize the quantities worked as an example. The function evaluated at x0, the function evaluated at a point slightly displaced, and the displacement delta x. Note that the slope of the function is evaluated at a specific point x0, so for every x0 chosen, you'll get a particular slope. This means that the slope is a function of x0, and as the name of the general variable values is up to us, we change it by x, so now x is the point where the slope is calculated. The last detail on how to obtain the exact slope is to get closer and closer to the point of interest, with the new notation and a specific x. The exact value of the slope at the point x is obtained by approaching the point and quotient with tinier and tinier displacements delta x, so we have to make this quantity as small as we can. This is making it tend to 0. We can now establish our definition. The derivative is the limit of the quotient we have discussed, as the small displacements delta x tend to 0, and it represents the slope or rate of change of the function f at some point x of a variable. Let's get back to the mountain example. If the height is given by the function x squared in terms of the horizontal displacement, we can obtain the value of the derivative at the point 1 meter by two methods. First, we can sketch a tangent line at that specific point, draw a right triangle, and divide its legs. With this, we know, at least approximately, that the slope at 1 meter is about 2. Then, by using the limit of the definition and a bit of algebra manipulation. Pause the video if you want to try it step by step. Note that we end with 2 plus delta x, and as delta x is something really small, tending it to 0, this sum actually tends to 2, and we can conclude that this is the value of the derivative at 1 meter. As we have said previously, the derivative returns a value for any x selected, so it is also a function of x. This is, we are able to get the general formula of the derivative for every point x. We have to use the definition and a bit of algebra again, calculating the limit at the end. Now we only have to evaluate this formula on the point we want to obtain the slope, and look at how this magic definition gives us the slope at any point. With this formula, we have established the derivative function. We can obtain the exact value of the velocity of Sonic with the definition and the expression of the position as a function of time. Here, the function f represents the position, and the variable x expresses a certain time. With this, we evaluate the key quotient, manipulate and evaluate the limit. We end with an expression independent of time for the derivative function, which means that the velocity is constant and equals 1.5 meters per second at any time. At last, let's detail something. As we have said previously, x is only a name for some variable value, so if the variable is time, it is convenient to call it t. For that, we only have to change the letter x by t in the expressions and the algebra done. Equivalently, any function could have a convenient name. For example, if the derivative function expresses the velocity, we can change it for v of t, to know that we talk about the velocity as a function of time. At the end, the most important thing is to know perfectly what each letter and notation represents. To summarize, the derivatives can be seen as a rate of change of natural things or processes where a function and its variable appear. They are also general functions that, given a certain value of the variable, gives you a specific value for the derivative. Finally, derivatives have a rigorous definition which enables us to calculate them and obtain general formulas.